Hi, everyone, and thank you for joining our call today. Hi, Giacomo.
Hi,
Hi, it's great to see a lot of people here. And Maxime, just go ahead with the presentation.
Hi, everybody. Today I would like to do a few technical updates. The call today will be quite technical regarding the effects that Taproot may have for RGB. Namely, we have a number of opportunities how RGB can be improved using the Taproot functionality, and the, 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 the aim of the call to go through a couple of rationales and discussions and take several decisions on of how RGB can be improved and in certain parts fixed with what Taproot gives us. And I would like to start with the announcement, a very pleasant announcement for me, that yesterday Rust miniscript made a first release candidate providing full Taproot support. And this was since the release in February of Rust Bitcoin. It was the last major obstacle on the way of RGB completion and release, because it wasn't just about it wasn't about the fact that RGB really needed Taproot. It was more about the fact that Taproot prevented a lot of different PRs required for RGB working to go into Rust Bitcoin. And finally, the version of Rust Bitcoin, which we've all been working for more than a year, was released. And after that, a miniscript on top of it was released yesterday. And in the following weeks, we plan to do a sequence of releases, codenamed version 0.6 of all our main libraries and products, which will start fully supporting Taproot. From this point, it will include the client-side validation libraries, descriptor wallet, RGB, LNP libraries, and nodes. And gradually, starting from the most foundational libraries like client-side validation and single-use fields related, and up to the RGB and Lightning Network. And the goal of the call today is to refactor a use of commitments, specifically deterministic Bitcoin commitments. I will explain why they are deterministic in RGB. And we will go through four main points, design points. The first, I would like to design the use of Taproot op return commitment scheme. And I would like to discuss the proposal of switching RGB exclusively to this commitment scheme, skipping the support of other commitment schemes. I will provide the rationale why for this proposal throughout the call. Second, I would like to propose to put all RGB commitments inside the transaction into a single output, because currently, if you have different RGB smart contracts in the same transaction, they will usually commit into different outputs, each one of them into their specific output. Change the selection mechanism of how we determine which transaction output contains RGB commitment, and use all of that to avoid interactive complexity, and I set privacy links which happen in Lightning Network and conjoin, payjoin protocols. So starting with all of that, I would like to first explain what are deterministic Bitcoin commitments and how they're different from usual commitments. The main difference between just a commitment and deterministic commitment is that with a deterministic commitment, we can prove the uniqueness of the commitment. We can prove that there is only one and the specific commitment that may exist in this particular Bitcoin transaction. So that's how, that's how they are different. And on the client-side validation part of the story, Peter Toth is here. He can also correct me or add to that story. Is that with the protocols like open timestamps, we just create a commitment, and we must know where the commitment is located inside Bitcoin transaction, but we do not have requirement that there must be only a single commitment to the data in this transaction. While with the single use based protocols like RGB and others, we must be able to prove that no alternative commitment exists, because otherwise we will have a possibility to double spend. So that's why we are talking specifically about deterministic Bitcoin commitments, and that's what deterministic word means here. Deterministic Bitcoin commitments, of course, are based on more generic commitment schemes. These commitment schemes by themselves do not have a provable uniqueness, but are used as a building blocks of the deterministic Bitcoin commitments. And specifically, we can say that there are three main types of commitment schemes: op return based, pay to contract based, and sign to contract based. And these commitment schemes have different varieties, and they can be classified into two main types. The first one are those where commitment goes into transaction output. We can call them output based. And the second one is are those commitments where the commitment goes into input. So they're input based. And there is only a single type of input based commitment, which are based on sign to contract commitments. Again, I wouldn't be going into details explaining how sign to contract or pay to contract works, because we wouldn't have time to discuss the rest of the story. So that's why I said that call will be quite technical, and it requires certain knowledge of these protocols already. The output-based commitments are more diverse. First of all these commitments started with a very simple scheme where you put the commitment in explicit form into a dedicated output containing op return code, which prevents this output from being spent, or keeping this, it prevents also Bitcoin Core from keeping the output as a part of UTXO map in the memory. However, it sacrifices use of blockchain space. Then a more advanced scheme was proposed, which is pay-to-contract commitments, where the public key is tweaked, and you don't need to add additional output or sacrifice any blockchain space. And the commitment is hidden inside the homomorphic tweak of the public key of one output. There was a modification of this commitment, which we designed for future Taproot in 2019, because in Taproot you can't directly tweak the public key present in the output, because it will break the protocol itself. So we put the tweak on one level below. So we tweaked the internal public key before it was instead of self-tweaking internal key, there is no script present. We tweaked the public key with that commitment value. And in that way, we produce the output key. But I wasn't quite happy with that scheme, because it basically, well, it's still Taproot compatible, but it breaks the idea that the commitment is hidden somewhere below another tweaking procedure, and what wasn't very simple to implement. So there is another commitment scheme, which is also output-based and which is compatible with the Taproot. And the idea of that commitment scheme actually came from the Bitcoin mail list. Somebody proposed that we can put op return code into the Taproot script, into the tree of Taproot scripts. And in that way, we do not need to tweak the public key outside of the scope of normal tweaking of Taproot protocol. So this is the landscape. And many different protocols uses different forms of commitment procedures. For instance, confidential transactions in Elements project and Liquid Network, they use sign to contract commitments, open timestamps using op return commitments, and in the future maybe they will switch to other forms. RGB, as of today, was planned to is using pay to contract commitment, and there were plans to use sign to contract commitment. We had a call last year where we also had Federico and Peter Todd and Giacomo, and we were discussing different trade-offs between pay to contract and sign to contract commitments. Actually, we can say that this call is a continuation of that discussion. Taproot by itself is based on pay to contract commitments to the script tree. Omni protocol uses op return, and so on and so forth. So basically, these commitments are widely used in Bitcoin ecosystem. And when we move from just commitments to deterministic Bitcoin commitments, we need to add on top of all these protocols and all these possible commitment schemes a very specific way. We have to uniquely and deterministically define a place where a commitment can be present in 3 levels: inside pub key or signature for pay to contract or sign to contract commitment, inside a script, because if you have an output that contains a script, and in Lightning Network, all outputs contain a script, you need to find a way how you can embed and define which specific public key among all the public keys of the used in script contain the commitment. And finally, inside that transaction. So to a proper deterministic Bitcoin commitment scheme must define which part of transaction is used for commitments. Is it input or output part? It must provide a deterministic selection of specific input or output number that contains a commitment. And it also deterministically encode the commitment into the output or input data structures. So, summarizing the discussion that we had last year, if we will have to select between the best part to contain the commitment among transaction input and transaction outputs, this is analysis showing in green the upsides and in in red downsides. And if we put the commitment into the input, we can really simplify detection of which input has to contain the commitment in case of single-use seal, because basically the input that spans the output that is defined as a single-use seal should have that commitment. So it's really simple part of the story. And you don't need to aggregate information from multiple parties if the transaction is constructed as a multi-party structure, for instance, like in Lightning Network or like in conjoin, payjoin protocol, because each input comes from a single party. This is the upsides. The downside is that the only commitment scheme that you have with the input is a sign to contract. And in fact, it is not yet compatible with the Taproot inputs because it has a lot of issues. We were analyzing them last year. We don't have any working scheme for music sign to contract commitments. We also do not know how to support post-Taproot, post-TapScript types of scripts, because Taproot allows more script types than just a TapScript. And these script types can be even keyless, or they may use different forms of keys other than key curves. So we don't know what it will be in the future, and we can't make it compatible with this future scripting. It is also not compatible with the spending, where you do not need to provide a key to spend the output. Basically, there might be outputs which can be spent without providing even a single signature. And specifically, it's not that rare because Lightning Network introduced quite recently so-called anchor outputs, which are spent without a key. And in that outputs, you can't put sign to contract commitment. And finally, it's really hard to make them compatible and working with hardware signing devices, because you need basically to modify the firmware, and these devices have to produce a proper nonce, non-random nonce, which actually quite a challenging task to do that securely. On the other side, with the output-based commitments, you have a lot of downsides as well. That's why we were thinking about adding sign to contract scheme to the RGB. The output needs interactive commitment construction in multi-party transactions, like in Lightning Network and payjoin. It leads to complexity and leakage of the information about, for instance, RGB assets that different parties have. It also has a complexity in defining output that contains the commitment, which output is used, and we will analyze that a bit later. and commitment always change the address. And because the address change, basically the wallet will not know which addresses belongs to this wallet, and it introduces a lot of complexity to deal with that issue. However, on the upside, you have a big selection of different commitment schemes to choose from, unlike sign to contract in the input. And today, in the single-use seals, the implementation that we are using in RGB, we decided last year to support both sign to contract and pay to contract commitment. However, the sign to contract scheme is still not implemented. And the reason why it is not implemented is actually that I tried to implement, and I discovered that it depends on the upstream work in the SecP library, including not just Rust libraries, but SecP library, which is used in Bitcoin Core itself. So it will take months of work to get it done properly. And also, again, it's not compatible with the music, and nobody knows how to make it, how to embed the design of a proper sign to contract commitment into music protocol, because music protocol is not yet completed in Bitcoin Core itself. So maybe it's not even months, but years of work for the upstream libraries to be able to bring proper sign to contract commitments to RGB. On the other side, in pay to contract commitments used in RGB today, we have three main problems. First of all, I tried to show that we made some design decisions in RGB that enabled us some upsides and good features. And on the other hand, this design decision has produced challenges and problems which we faced when we tried to do a practical software working with RGB. So first of all, in RGB, we select the output that contains commitment based on two factors. First, the fee of the transaction, and the second is the identifier of RGB smart contract, which change in state we are committing to. And basically, this allows us to avoid a chain analysis because you do not able to predict which output contains commitment to which RGB smart contract without having the client-side data. And basically, the way it worked, we add the fee in Satoshis, total amount of Satoshis spent on fee in the transaction, to the transaction, to the RGB contract identifier, which is a hash, and then we modulo this number on the number of outputs, and we get a number of outputs which has to contain the commitment. That makes the scheme deterministic, and it combines the two factors, one of which can be assumed from the transaction, actually from blockchain, and the other can be taken from the client-side data. So we thought that we spent a lot of time in 2019 with Giacomo and the rest of the community designing this specific way of determining which transaction output contains the commitment. But I have to say that probably it was one of the largest problems which we had in actual RGB implementation when we were trying to integrate RGB with the wallet, because the amount of complexity it introduced was tremendous. First of all, the problem that if you spend a couple of inputs having different RGB assets, or an input that has a number of RGB assets under different contracts, you will end up that if a transaction have 2 or 3 outputs, each of them has to be tweaked, and each of them will contain some part of the commitments. And you will have that you wouldn't be able to pay to somebody to some address if you was provided an address to pay to. This address will be changed, and you will have to increase the number of outputs, hoping to separate all these commitments under different RGB contracts. The second, you have to readjust fee level to do the same, and it puts you into recursive cycle where you change the fee, you need to change the amount, you need to change the number of inputs, And this may lead to the fact that you will change the number of assets that you're putting into the transaction, which will change the amount of commitments you need to produce. And like, it's really hard to implement in a proper form in RGB Vault. And basically, that's quite a complex story, which we faced when we were implementing wallet libraries. And finally, the final problem is that we designed a way how we can tweak any type of transaction output, pay to public key hash, pay to witness public key hash, and so on, pay to script hash, pay to witness script hash. So all outputs, types of outputs are supported, because it was required such that if we use a fee plus protocol ID, we can't guarantee into which type of output the commitment should go. And that's why we need to support all types of outputs. For instance, like in Lightning Network, we need to support scripts and outputs. And it resulted in a lot of complex code being developed, supporting different types of outputs and including also script support, which is really hard to audit. And of course, all this code increases the attack surface. So, we released the prototype of RGB with all these pay-to-contract commitments working in this complex way a year ago, in May 2021. It was named RGB Core and RGB Node version 0.4. And we built consumer-facing products with that. It was a set of wallets, My Citadel wallet, which was a mobile application, iPhone, iPad. It was a desktop wallet, and it was also a command line wallet and server-side wallet, just to try that RGB works under all these environments. Bitcoin Pro, which is a tool for asset issuers, and RGBX.io, which is a website to list the issued assets. And what we found out that the complexity of wallet implementation due to this commitment scheme was tremendous. And basically, because I was writing this My Citadel wallet from scratch as a Bitcoin wallet, first of all, and of course, adding support of RGB to it, I have to say that I spent much more time on implementation of everything that was required by pay-to-contract commitment scheme and the RGB commitment scheme, then writing the whole Bitcoin wallet by itself. So integration of RGB into Bitcoin wallet takes more effort than to implement Bitcoin wallet without RGB from scratch. So that is actually quite undesirable. And this part, if we will go back to this story, where we analyzed where to put the commitment, we end up that it's only possible for RGB to use the output for the commitment. But if we use pay-to-contract and existing scheme, it is really complex to do a proper, efficient wallet software with it. And inputs can't be used because sign-to-contract schemes will be ready for usage in a year or more than a year from now. So that's why it's not applicable for RGB and single-use seals as of today. Maybe it will be applicable for other types of deterministic Bitcoin commitments under different protocols, but basically we end up with this story. So what to do? We again ending on the same page we started from. And that actually brings us to a set of proposals that I would like to discuss with you and find out maybe they will be able to solve all these issues. So the proposal is that to move step by step and solve each of the problems that we have with RGB today, with RGB pay-to-contract commitment. In output basic commitment, we have problems in RGB with a pay-to-contract commitment, and we will try to find out, can we use some different commitment scheme based on commitments in the transaction outputs, which will let us to avoid all these problems. And three main problems we are trying to solve is, first of all, wallet and HSM integration complexity and compatibility. Second is the problems with multi-party transactions, like in Lightning Network and conjoin payjoin protocols, where we need interactivity setup for the RGB part, and also need to disclose the information about RGB assets owned by each of the parties, even if these assets are not transferred, and the complexity of implementation of the protocol libraries themselves. Let's start by looking at the components of a deterministic Bitcoin commitment landscape. So what protocols and parts of the protocols we do have? Again, we have on the left side the output-based commitments and the right-hand side input-based commitments. And we have two basic forms of the commitments. Pay-to-contract, where we tweak the public key for pay-to-contract, pay-to-public key, pay-to-public key hash, pay-to-witness public key hash output, or we tweak a set of keys present in the output script. It can be either bear script or pay-to-sig script hash, pay-to-witness script hash script, doesn't matter. So there are main two options, how we can tweak the output with a pay-to-contract. And for input scheme, we have a ECDC-based sign-to-contract, the technology that is being already well developed and used widely. The only problem that in Rust libraries, Rust XP libraries, they are not yet implemented. So to use them, we had to implement them. And sign-to-contracts are got really extended with the introduction of Schnorr signatures. And these all protocols which need to modify need to tweak Schnorr signature or a set of Schnorr signatures in the transaction input, including the case of MU6 of aggregated signatures, are non-existing. These protocols still has to be designed. Also, we have op return, this ancient commitment scheme we started from, which doesn't require tweaking of public key. And finally, the most promising story, we will be focusing much of our time on it now, a tap return, that proposal of putting the op return commitment inside the tap tree, inside the Taproot script tree of the transaction output without modification of public key. There were also other hypothetical schemes which I will mention. My analysis has shown that they are not usable, or it's not advisable to use them. We can, for instance, put input commitment into annex. Annex is a structure inside the witness introduced by Taproot, and this structure has a consensus meaning. However, this consensus meaning is not yet defined, and it will be defined in the future soft forks. So to put the commitment into annex is really bad idea, because we do not know how it will be used in Bitcoin consensus. Or we can just add stack items to the witness, which are not used by the validating scripts, but it's also a very bad idea because basically, first of all, it consumes the on-chain space, and secondary, it may undeterministically interact with the script logic itself. So we probably need not to think about this way of doing things. And additionally to the commitment scheme, deterministic Bitcoin commitment defines a clear definition which output contains the commitment. And for that reason, we need a set of protocols which determine a single transaction output with the tweak. And in RGB, as I said, we use fee plus protocol ID. We can also use just a fee to find the transaction output containing the commitment. We can also overload some meaning of some bits in sequence or in log time numbers. Or we can stick to a protocol that says that commitment is always located in the first or the last output of the transaction. So this is all possible options that we have on table to do deterministic Bitcoin commitments. And now I will start with analyzing what can be used out of them and what can't be used. And the fee plus protocol output selection, I will start with the selecting which output contains the commitment. I already described this slide before, that we introduced this to dynamically select output and improve resistance to chain analysis in 2019, but it really worked bad in practice. First of all, it requires access to blockchain, because to do the fee computation, we need to extract not just a single transaction, but also all transactions which output we are spending. and it complexifies all parts of the wallet software, basically, which work with RGB verification. It makes transaction construction recurrent and complex, and with multiple RGB contracts present in the same transaction, it makes impossible to pay to specific address, since all outputs get tweaked, and still requires interactive protocols, which leads to private data leakage. So we say that probably it's the part that we have to get rid of, and we need to use some other form of deterministic definition of the transaction output with the commitment. Also, I will remove these hypothetical protocols which are not really usable in practice, as well as Schnorr Taproot-based sign-to-contract protocols, which are non-existent, and it's really hard to design them properly, as well as the rest of the sign-to-contract protocols as we described previously, because even those ECDC-based sign-to-contract protocols requires months of development in the upstream libraries. So we end up with just output-based deterministic Bitcoin commitments. And the fee itself, without the protocol ID, is also quite a bad idea, because we still have nearly all of the problems that we have with the fee plus protocol ID protocols. So we end up with the pay to contract or return to contract commitments, and two main options: using NSEC or log time number, or using the predefined output number. So let's choose between the pay to contract or return to contract options. Well, pay to contract option has a lot of drawbacks. First of all, it requires wallet to keep track of all key tweaks, and these key tweaks are needed for both balance computing and for spending outputs. And it also makes very problematic to sign the spendings with the hardware wallets, because wallets need to tweak private keys to spend the output. It is possible, but really complex. And it requires firmware updates, and it's not compatible with the outputs that can be spent by anybody, like in Lightning Network, because we do not have a public key to tweak in that output. And it leads to a complex management of the multi-sig wallets, because also you have to have, as a part of the protocol, the decision who has to tweak his keys as a part of multi-sig scheme. We found a way to mitigate most of the problems related to multi-sig wallets, but still it just increases the protocol complexity. And the only positive side is that it is compatible with all output types. As about the return to contract options, which is op return and Taproot-based op return, we still have to track the commitment, the values of the commitment we add to the output, but we need that only for balance computing and not spending, because we do not spend op return output, or we do not spend Taproot output via op return containing script branch. So these tweaks are never used in spending. This actually removes the problem of hardware wallet compatibility. Hardware wallets do not need to tweak public keys or private keys to spend the output. And it is very well compatible with anyone can spend outputs, basically, because if you put op return into Taproot, you still may have different script spending paths which do not contain public keys, but can be spendable with a hash per image, for instance. It doesn't affect.
Sorry, Maxim, may I ask you a question?
Yeah.
If you want to ask later.
No, go on. It's better to jump in.
So, so is it that hardware wallets do not need to tweak now, or they already need to tweak the normal Taproot tweaking in the first place? So we are basically delegating the tweaking complexity that will be facing other wallets to the Taproot habilitation itself. But in a way, if you spend a Taproot output, which any use of TypeScript with or without op return inside the TypeScript, you will need the hardware to tweak the general basically they already have to tweak the key for Taproot itself in a way.
Yes, they have to tweak the kit for the Taproot, but the tweak is produced inside the hardware wallet from the data which are available to this wallet. Unlike
okay, so basically we are delegating the complexity to the thing that the hardware wallet providers will have to do anyway for standard reasons using Taproot. Great. Okay.
Yes, and the hardware wallet do not need to produce op return commitment inside the Taproot by itself. It is produced outside of the hardware wallet, so we are not even delegating. The hardware wallet actually does nothing at all additional comparing to signing just a normal Taproot output.
Great, clear. Thanks.
So still, the Taproot, the hardware wallet probably will need to display the information that this transaction contains some RGB asset spending, but it is not part of the signature procedure. It's just a part of the safety procedure, which is very different. And also the op return inside the Taproot does not affect multi-sig wallet management procedures anyhow. So basically, you still produce the joint aggregated signature or separate signatures in the same way as you do without RGB and any commitment. And the only problem, the main problem with that, is that this type of commitment scheme compatible only with specific output types, namely op return or Taproot outputs. You can't put it into arbitrary output. So with that, we can probably get rid of pay to contracts as a part of the solution to the problems which we have to RGB today, because actually all the problems we have in RGB are related to pay to contracts, and end up with these two options. And now I would like to explain how the actual commitments inside the op return, inside the Taproot should work. Because it's not just that we can put a commitment into any part of the script tree. We have to have a determinism that the commitment has to be present in a well-defined singular place, such that we can't double spend. So that's how it is different from just an idea of the deterministic Bitcoin commitments using op return and Taproot is different from just an idea of putting any commitment with op return into Taproot. And the design that I propose for that commitment scheme is to add the rightmost node to the script tree. So basically, let's start, maybe not everybody knows how the actual Taproot works. The Taproot output is constructed. The idea is that instead of a single script in Taproot, you have a set of scripts. And these are scripts either. So the output can be spent by satisfying requirements of any of these scripts. You can satisfy requirements of script 1, of script 2, of script 5, or 6. Any of the satisfactions will allow you to spend the output. And these scripts are constructed into a structure called Huffman-Merkle tree. This means that it's not that they are all on the same level and then you Merkleize them. No, the script leaf can be at any level of the tree, and the way you order the scripts by the probability of spending. So the condition under which you most probably will spend the output should reside at the top level. Then less probable condition goes on the level below, and so on and so forth. Because each time you spend the output, you provide as a part of the witness a structure called control block, and that structure contains the Merkle path from the script you are using to the root. And the more deep script is located, the larger the data structure inside the witness, and more fee you pay and more block space you utilize. So basically each path of the script tree is 32 bytes. So if you go to the level 3, you already have to present 32 multiplied by 3 additional bytes to spend that script condition. And the best place to put a deterministic commitment is the longest chain of Merkle paths, because it will be never spent. You can't spend the script containing op return code. So you will never put into the witness the Merkle path. And also, the tweaking procedure happens when the tree is already constructed. So you need to have a simple procedure of how this tree will be modified. So you have just two options: to put the commitment at the most top level, left side of the graph, where we have a script one, but this will require to recognize the whole tree, and also it will increase the amount of the size of the witness you will be putting into blockchain when you will be spending real script spend conditions. Or you can put it at the deepest level, as here, add another node, and we will have the longest spending path, but you will never reveal the spending path in blockchain. You will only keep the spending path in the client-side validated data. And the last script will be this op return script, and the Merkle path will be part of deterministic Bitcoin commitment proof, proving that this specific output contains this specific commitment. So the algorithm is the following. To commit, we add rightmost tab script with op return to the tab tree. Tab tree is this structure of scripts. And the only complex part here of the story is that how you organize which script is on the right side of the node and which script goes to the left side of the node. The way you do it is by comparing the value, lexicographically comparing the value of the hash. It's part of BAP 341 standard, defines it. And if the hash of this commitment will be smaller than the hash of this, they have to be switched places. And this breaks determinism, because you wouldn't be able to prove that the other path doesn't have some other commitment. So the idea is that if we will meet condition like that, such that the commitment, the hash of the commitment is smaller than the hash of real script at the bottom node, we will just do the following. We will add another node and another script, and this script will be a hidden script because Taproot allows us to do that. It will be not an actual script, it will be a hidden node containing the hash of this data -1 numerically. So it is probably non-script. It will be also never used, and it allows us to put the real deterministic commitment into top downmost right side place, which was that place where it must be present. So it has to be present. So that is also the part of the procedure. I defined it here.
Sorry, regarding this, could we also maybe just duplicate the commitment on both sides of the branch? Would there be any advantage or disadvantage in doing that?
I think that I don't see any disadvantages of doing that.
Replicating may be similar to the standard merkleization process where you have an odd number of leaves. So maybe it could be, well, it doesn't seem to change much, but it could be more, in a way, closer to the merkleized leaf duplicate. So I don't know, but it could be a good idea.
Yeah, and actually we can save some client-side space, because we will duplicate the node, but we can signal this duplication with just a single bit or byte, not necessarily spending 32 bytes of storage. Yeah, so good point. Then we update the rightmost Merkle path, Merkle root, and output key. So we need to update everything up to this level, which is quite a simple procedure. And after that, we keep and store the internal key, the Merkle path, a new Merkle path, to the rightmost commitment node as a part of the proof on the client side. And to verify, we take basically commitment value from the message we are committing to. We take the Merkle path and internal key, and we replicate this procedure. We create op return containing the commitment. We hash it. We check that, and we check that we can build the same Merkle tree and the same output as present in the transaction mined in blockchain. So basically, we rebuild the output and make sure that it exactly matches the output present in the on-chain transaction. And that is verification. So the procedure is quite simple. I have to point out that there is some simplification here, because basically the path that you're saving is not the hashes of these nodes, but instead it's a hashes of these scripts, because you add hash of these scripts plus hash of the commitment, you get this node. Then you add the node plus the hash of this script and you get this node. So basically this is the Merkle path, not these nodes. But it's just a small technical nuance.
Just one thing to go point out.
Yeah.
In this, the idea of Huffman encoding, keep in mind, isn't actually in the there's no requirement for the Merkle tree to be Huffman encoded in the actual consensus, right?
No
and
requirement.
Yeah, and I'd point out, it's just not clear to me why exactly you absolutely have to have it as a lowest possible element. I mean, it seems to me that it'd be fine to just
not lowest, rightmost. Probably the proper term is rightmost.
Yeah, which I mean, it seems to me like it'd be much simpler to just go say, just say it has to be the first right element and call it done. Like it's just not clear to me. You really do need.
It could be a poorly balanced Merkle tree, like this one, really poorly, and the commitment that we have, you just have to be this commitment. So it's not the deepest one; it's the rightmost.
Well, think of it this way: in most cases, there really is going to be just one spending path anyway. So you're not actually adding. If it's a simpler rule, you're not actually adding any more on-chain data in the standard case. I mean, the vast majority of these are going to be spent using the the simplest possible signature. So I'm not sure that actually makes much of a difference.
So for a simple single script path spending, we'll end up with this structure. Left, you will have a script. On the right side, you will have a commitment. If the Taproot output doesn't contain any script path spending, you will end up with this commitment and commitment.
Yeah.
So these are all cases. So basically, you use the rightmost path. It's just the way it is advised to structure the Merkle tree as a Huffman, such that the most probable script will be always on the left path. But if you such that you have just a single step of the Merkle path. But if you structure it in the wrong way, like this, you still have the determinism that the commitment is here, and to prove the commitment, you will need the value of these nodes.
But what I'm saying is, if you simply go and say that for this purpose, the commitment is always on the first right hash, then you don't have to go deal with providing proving the commitments above it. You just have that one deterministic thing and you're done. And that doesn't add much big difference
because it's not stored in the blockchain.
No, but my point is the code to go prove that is much simpler because you're not proving a path of a Merkle tree.
Oh yeah, absolutely. That's the idea I was proposing.
Yeah.
So you always have just a single path which is rightmost. You know that your node is always on the right side, on the all of the path.
But there's an even simpler version, which is say the position within the tree is fixed to be the top, to be one level down on the right, done, right? That's the simplest way you can go do this.
No, because you actually, it's not the simplest way from the wallet perspective, because the way it works is wallet constructs a PSBT with a tree, and it probably doesn't expose the whole tree to you. And the only option that you have is actually to add more node at the bottom part. You can't modify the anatomy of the existing tree.
Wait, so you're saying that like there's existing wallet code that out there that has this property?
Yes, like Rust Bitcoin, for instance.
Okay, well, yeah, all right, scratch that then. That's kind of annoying.
Yeah, I will be. It's very annoying because basically I spent a lot of time on this, fighting this issue, and I will be saying at the very end of this presentation that how actual PSBT workflow works with Taproot and how it has to be modified to work with the deterministic Bitcoin commitments. Because you end up that basically the creator and constructor constructs the tree, and the commitment happens by a different participant even. So he may have not full access to the tree itself. So the idea was to design the protocol such that it always can be tweaked from the information present in PSBT, the actual PSBT. So we end up with having top return as a main way for RGB commitments, because it seems to be quite simple, robust, still leaving us with a number of
wait, regarding this, so would you get rid of the simple op return option aside the
Yes, I will get rid of simple op return option due to a single factor, because it adds nothing to having just a top return option. No advantages, but still complexifies the code that actually does the commitment or validation.
Well, I will say that one advantage could be for, wallet developers to have a easier way to implement this without dealing with Taproot if they want to.
So for non-Taproot, for legacy wallets which are not Taproot in general, but at this point, I don't know, maybe we can assume that, it will basically cover
integration of RGB into wallet much higher than complexity of integration of Taproot anyway. So maybe it would be a good driving point to put them together.
Force.
Of course.
If you want RGB, you need Taproot.
Yeah, that was one of the ideas to discuss. So maybe we can go after that. Because op return is really poor design. And people, if we will let wallets use RGB without Taproot, most wallets will take years to do the Taproot, but some of them will run after the RGB plus NFT tokens, whatever cheat, and we will end up with a situation where we just multiply the number of op returns in the blockchain.
Well, I mean, if that happened, it means that there was an advantage in providing this only op return option. I mean, that a lot of people that wouldn't have implemented with Taproot, they did it with op return. So maybe it doesn't help Taproot, but it will help RGB adoption, I guess.
I'm interested in Taproot more than in RGB.
Oh, well,
Taproot adoption more than in RGB adoption.
Yeah, but okay, but I don't think
the
goal of RGB should be to boost Taproot adoption. Sure.
Yeah, well, it's also the question to consider. So it's the proposal we will discuss at the end of in a few slides from now. So my proposal is just to stick with the top return commitment scheme and not other schemes. The next this decision that we have to make is to choose between two last output detection schemes. First, based on n-cycle lock time numbers or on a fixed output number. And here is the comparison between them. So if we will reuse, reutilize, and sequence and lock time to point to the output that contains the commitment, first of all, it can collide with possible future consensus of forks, assigning different meaning to that bits. And it's quite hard to design it in a way that will prevent on-chain analysis and not interfere with the way it is used in Lightning Network and so on and so forth. If we stick to the first last output, the downside is that it's also hard to mitigate chain analysis, because we will put the commitment into, in most of the cases, into the change address. We will put the change address into specific position in the transaction, which has to contain the output. So it will be the first or the last position. There are some mitigation to that. For instance, that we can signal the output number in single usil definition in the client-side data on the previous round. But it's quite risky, because, for instance, let's say that when you define a single usil, you put 1 byte with a number from 1 to 256, and this value will be used when you create the transaction. You divide the number of outputs, you divide this number modulo number of outputs in the transaction, and basically you get the output that will contain the commit. But you don't know the structure of the transaction you will be creating at the moment when you create a single usil. And you may end up with quite complex wallet design that has to take into account that number in constructing the transaction. And especially in multi-party transactions like conjoin, payjoin, or HTLC, Lightning Network transactions, when the number of outputs grows rapidly, and the number of outputs is defined by the protocol state, it also makes the scheme quite complex. Or you can add another mitigation to the chain analysis to add more change output, which will consume on chain space. So basically, all options here are bad. And that was one of the reasons we stick to the fee, the use of fee in that process, use of fee plus protocol ID. But basically, the first taproot output in the transaction must contain the commitment. And this will still allow some forms of chain analysis, because it will point out that the first taproot output is usually the change output. So this is the open question to discussion.
So first of all, one of the reasons we could not use the previous single usil, if I remember correctly, is also that I could just send transactions to myself many times before sending to you in order to double spend. So I can basically I can attack before just sending to myself several times and creating 2 stories. I seem to remember this kind of attack, but anyway.
Yeah, but it's not related to that. It's more like we clearly need to deterministically define which output contains the commitment. Otherwise, we don't have double spending prevention. Oh, you mean that in the single usil?
Yeah, in the single usil case, yeah.
No, that's not an attack, because each single usil, each time you close single usil, you commit to the new single usil, and you have still history that is deterministic. Like, you can't create alternative history. If the transaction is mined, it has a commitment, and the part of that commitment is the number that we use in output definition.
Well, let me go point out something, which is that you can define a standard where the commitment can always be committed to in exactly one output for no matter how many participants are in the transaction, by just saying that what they're committing to is a Merkle tree keyed by, whatever type of data they particularly need.
Once again, you are committing.
All right, so
yeah.
So suppose I have a protocol where I need, multiple. The act of spending, one or more multiple inputs have some committed meaning in such a way that what that meaning is can be arbitrary, and I may have multiple protocols at once. you can define a protocol where, as an example, you just have one single op return output, and then you, in that output, commit a Merkle tree of, keyed by a protocol-specific hash derived by, hashing some data about what you're trying to do in some particular way, right? And the point is, if you do that, that Merkle tree can be built by all participants in the transaction. So in the case of a complex conjoin, so long as you have a system where, the conjoin participants know what all the inputs will be in the beginning, they can agree on a common Merkle tree by building that Merkle tree up, right?
This is exactly, that is exactly that slide you're probably talking about. So basically, the idea is that under the same RGB contract, you have multiple state transition created by different participants.
Keep in mind, I'm not limiting this to RGB. I'd say you can define a protocol where for any type of protocol that needs this kind of feature, you would have a way of committing to essentially a topic and a key or in a value associated with.
So if I'm getting you right, basically we have a protocol already called defined in LNPBP 4 standard. Just give me one moment, I will open it. And it seems that this is exactly what you're talking about. And this works already. It works already with not just with RGB, but the whole idea is how to multi-message commitment scheme. Yeah, so it's already there. So, but this is a solution to the problem how to put multiple commitments into the same output, and how to make.
So hang on. I'm arguing something subtly different, which is that I'm saying that you can commit to the meaning of the transaction with one output, but then the outputs that would use to create single-use seals for then future actions do not have to be the same output. Right? Because you can commit to which output you want to go use as your single-use seal for the next step in the protocol, separate from the output that you use to actually commit. I think that's a key detail, right? And once you have that, there really is no need to bother with nlock time or fees or any other way of signaling which output. You just say you have one generic standard and you leave it at that, and it will certainly It certainly is hard to integrate that into arbitrary, say, conjoin implementations. But any implementation that was designed to have that feature, you can see it, doing that.
I'm not sure that I'm getting the design. So let's start slowly. I'm defining a single-use seal. It can be anywhere in the blockchain, just a UTXO. And when I spend that UTXO, I'm creating the commitment to certain message. And I need to define into which output of the transaction spending that UTXO commitment will go. So that's the way it works now. How you propose to modify this specific way?
So what I'm saying is, rather than doing things like trying to signal which output is the next step in the protocol with in transaction data, if you have a standard where you can commit, where you can build an arbitrary Merkle tree of commitments by topic, then you can always just pick arbitrarily which transaction output you want and just commit to that data in that one standard, right? And the point is that this gets rid of issues around conjoin and so on, because once you have a single standard for this, it doesn't matter what two protocols you're trying to join together. You can just say, hey, I need this key value in the commitment tree and leave it at that.
Giacomo, Federico, can you help me parsing?
No, the point I don't understand is still the same. So in this case, Peter, the information about the specific choice of output made following the protocol is inside the off-chain consignment. So
that's the key thing. It would be part of basically the proof that you had followed the protocol correctly would be your path up the Merkle tree for the designated output for the master like operator output or whatever it is, and then at the bottom of that Merkle tree, the particular data saying like what you were actually doing. So that proof might be all right.
You propose, so basically you create some operator in the blockchain with a tree where you have a certain place for each of the protocols, and there you commit which each protocol commits to which output it does select, and they can update that information.
Yes.
Oh,
and
like
in
elsewhere,
practice,
even in other transaction, like elsewhere potentially.
Yeah, absolutely unrelated. So basically,
well,
the protocol
and a key point
parameters.
being, a key point being is, for example, if you wanted to have the next, transaction output in your protocol, in that step of your protocol, be something entirely different, you could do that. Because you just say, hey, for my, for the next step in this protocol, I want the single use seal to be this particular one, maybe create an entirely different transaction, or to have a special signaling, say, well, I want to create, use the, say, 7th transaction output of the transaction this step was committed to. And, both ways are fine. But the important thing is, like, once you define that, it's reasonable to then ignore everything about, fee tweaking and end lock time tweaking and end sequence tweaking and all this.
But you don't spend more block space in order to fix. I mean, you can do that like differential, like it stays the same until you change it because you needed to change it, right?
Well, the important thing is, like, no matter how many protocols or what you were doing in that one transaction, you can commit to it all through one op return.
But do you need to add op return to each of the transactions?
Well, I mean, the simplest way to implement it would be to have an op return in every transaction in a defined place with 32 bytes and just call it a day. Now, obviously, you could also say, well, the first Taproot output, and then commit to that thing in that way. That's fine too. But the simplest possible way to do it would be to just use op return.
Yeah, op return is the simplest. Well, you basically can put commitment into the op return itself, and that's all. You don't even need
in particular, a commitment to the tree of commitments.
Yeah, but why do you
all
need
the
that if you
inputs are
already have an op return and you can just use this op return to store the actual commitments on the different protocols?
But hang on, but no, not store the commitments. Commit to the commitments. Right?
Yeah,
I'm saying the op return would.
Yeah, not store. Yes, commit to the commitments. Yeah, we have Merkle tree. So basically, the commitment we are putting into the transaction in these protocols, in deterministic Bitcoin protocols, is not the commitment to RGB at all. It's a commitment to a Merkle root of Merkle tree of commitments, where each of the commitments inside that Merkle tree is actual another commitment to a linear structure of the commitments coming from different inputs, and they're
not linear. A tree of a key value tree, not a linear thing. A key value tree of all the commitments you would want. Right. So the way the protocol would work is would say, all right, hash the input, the TXID that you're spending with some other per protocol, identifier, and then also and then that is the key in the Merkle tree, and then the particular bit of data that you actually want to go do something. Commit to would then be the value in the Merkle tree.
Yes, correct. That's how it works, and you end up with a single commitment under multiple protocols, which will be put into a single transaction output. That's how it works right now. The only question is how to define which transaction output will contain this Merkle root of all the commitments.
Yeah, and the key thing being, if you just always define it at, in the same place, like either the first or the last transaction output, we're done. We don't need to muck around with end sequence or anything.
That's the proposal. But the problem with that proposal that it allows chain analysis, because chain analysis software will know that the first or the last output is a change output, because you will put the commitment into your change output.
Well, but if you make it deterministic. Yeah, we could be saying that if you use on-chain data to decide which output you're using for commitment, then chain analysis companies can identify it quite easily.
Well, it wouldn't be able to identify the commitment, but it will be able to guess the meta information. So if, for instance,
so they will still figure out
commitment
it's the change
protocol
output.
gets widely used, the commitment wallets will always put the commitment into the change address. Why? Because the commitment changes the address. So if you put the commitment into the address you're paying to, the receiver wouldn't be able to see the payment. So you will always put the commitment into the change address. And
I agree, but
hang on. But in these types of protocols, the receiver doesn't even like. You talk about receiver is in a particular output, but
Bitcoin
these
payment receiver. So
right, but I'm saying. But point is, so in these types of protocols, when you actually use them, there is no Bitcoin moving. Like there doesn't have to be any Bitcoin moving to anyone else, right? Like you can use these as, hey, I have an existing transaction output that I'm using for single-use seals. I give it to you. I tell you, please go commit to that output in the off-chain data, and then we're done, right?
Yeah.
And when that happens, chain analysis is completely defeated.
Yeah, but it's absolutely different part of the story. So you're talking about defining single-use seals, and I'm talking about closing single-use seal over a message. So there is no problem with the single-use seal definition. You just commit to UTXO or anywhere in the blockchain and put that into client-side data. But when you close this, yeah.
But I'm saying when you close a single-use seal, into the protocols where you take an existing TX out you have, there is like chain analysis can't do anything about this anyway, because they just do not know which output, what was committed to. It's impossible to know.
Well, they know that the first taproot or output is committing to the message.
But you're missing my point. Is that in transaction, in protocols like this, what you would actually expect to go have is to have, exactly one output in the transaction, or two if it's like an op return plus, an actual output, right?
You mean that these transactions wouldn't be actual Bitcoin payment transactions, so there will be no change address?
Yeah. There's no chain analysis to worry about here.
But that's the bad story, because transaction with a single input and single output, or multiple inputs and single output, will again help, or two outputs, one of each op return, will provide meta information.
Well, but again, there wouldn't be two op returns. It'd only ever be one, right? So all chain analysis,
two outputs, one of each op return and just one normal.
Right.
It's still
but the point is, chain analysis isn't learning anything about where the value was transacted in that output.
Yes, I'm not talking about that. I'm not talking about chain analysis learning that part of the story. I'm talking about that this can be a basis for censoring certain transactions, like trying to make miners not accepting transactions fitting certain criteria. So basically, you create a set of transactions which can be clearly distinguished from the rest of transactions in the blockchain, a fingerprint.
Well, I mean, in reality, most of the transaction will be one input, one output, but that you just pay the fee and you commit. And so what are they going to censor transaction that send or move all the money to another output? I mean, it's a very generic kind of transaction. So I don't see it as a big problem.
Yeah, I don't see that as realistic either.
So basically, we can stick to use the first output or the last output or the first taproot output or the first op return output as a place of the commitment, and you all think that it is the best option if we look into this.
So just to recap the origin of this madness, because it's also my fault. The origin of this madness was trying to argue that you can eventually, in a high fee scenario, neutralize the block space consumption of the scheme, because the idea was, if you want to close the single seal, you just have to wait that you already have to send a Bitcoin transaction to somebody, and you can basically use your own change, because you still have to send yourself change in a typical transaction, and you can use that in order to close the seal. So the idea was about future-proof block space saving. If we don't rule important for now to have a strong block space saving, all this idea of using the change to send Bitcoin to yourself in another transaction and leverage these to also close an RGB seal, it becomes a little bit redundant. So it was all Luke Dashir approved kind of effort long term, which may be completely out of our realistic scope for the next few years.
Yeah, because from the wallet, yeah, go on.
And I mean, with aggregated seals, that does such a better job of that anyway, so I don't think that's worth worrying about.
From a wallet perspective, it's really hard to combine two payments into a single transaction, especially one RGB-based payment and the other Bitcoin one, waiting with RGB payment until you need to do some Bitcoin payment and then merge them together. From the user interface perspective and user experience, it will be just a nightmare.
I mean, notice how few
so
wallets even do merging of payments anyway. So
yeah, exactly. So it would be a theoretical saving, which would be practically impossible anyway. So we can go back to the assumption that we are not really saving space with another Bitcoin transaction.
So basically, we can stick with having just a first Taproot output used for the commitment. First Taproot output used to put the op return commitment to the set of protocol Merkle root of all the commitments, and do not try to engage with the NSIG and block time. So I assume that it would be the case. That's why I said wrote here that basically it's the best option, and I'm happy that we are more or less okay
yes,
with that.
And if we don't know, or if we don't do all the block space saving stuff, people cannot infer that Taproot output will be the change, because it will be not needed anymore. It will not be. Okay.
It may be only a case of censoring the transaction that contain a single output. But you can make this transaction to be aggregate transactions. Like usually this transaction will contain multiple inputs because of the coin selection, especially for RGB. And it's a normal transaction when you have multiple inputs, a single output. So I think that is fine. Moving forward. So the summary of the proposal is to switch from the current pay-to-contract commitments, which are described in 3 standards, 1, 2, 3, LNPBP 1, 2, 3, and which are used by RGB these days.
Maxime, sorry for interrupting. Are you showing the slides?
Yes. I was showing all this time.
Well, right now I don't see them, so maybe you can turn on.
Was it long time?
No.
No, just a few minutes.
Okay.
Yeah. Okay. No, it's better.
So that's where I showed that we are burning out the idea of using NSIG and landlock time to define the output with a commitment. And the feasibility analysis of switching to tap return. The proposal is to switch from the current pay-to-contract based scheme, where you can tweak any output in the transaction, and you define that by using fee and protocol ID. It has a lot of downsides, which I all mentioned. While with the Taproot based op return commitments, it will be, I will write the standard for that, and we will ask all of you to peer review it. But basically, it will be just the detailization of the idea that I described on the slides of explaining how the protocol will work. And it have just one downside, that it will be compatible only with the Taproot enabled wallets. This can be mitigated by the enabling also op return, bare non-Taproot op return commitments. But my proposal is not to do that and stick just with the Taproot. Because first of all, you are not, it doesn't mean that you limit the outputs which may contain RGB assets with a Taproot outputs. No, you can assign RGB asset to any output, which even may be existing for 10 years for now. You take so. It's just the commitments to do the RGB payment. A wallet must support creation of Taproot output. And the idea is that it can drive adoption of RGB. And also because we need to modify the Lightning protocol, we are modifying Lightning into Bifrost to support RGB anyway. That's a good opportunity to bring the Taproot into Lightning network as well. And the rest is just upsides, because we just tweak a single output in a transaction, and we don't create a lot of problems related to that. And there is no interactive protocols required. No need to change hardware, wallet signers, simple streamlined code, and no recursive fee adjustments. So that is the proposal. And I think that throughout this presentation, it's quite clear that it looks good. So if any of you have any counter arguments of doing this switch, probably let's discuss them.
There was a question in the chat from Tricola. So is it right that we always use one input and one output?
Is it, sorry, what?
Is it right that we would always use one input and one output?
Well, it depends on how wallet will be actually structured. So the wallet developers can create any wallet. That can even create a payjoin transactions. But the real use case would be that people will be paying, if they will be using RGB assets to do a transfer, to pay, for instance, with USD Tether somebody, they will just take an output containing sufficient amount of Tether and will create one output which will contain the commitment for the whole payment story. And it will also receive all Bitcoins from that input, but these Bitcoins are not moving. They will move from one address of the wallet to the other address of the same wallet. But nothing prevents wallets from using more complex coin selection algorithms such that they will grab a multiple outputs containing small amounts of USD Tether to have them collected together, or create some other structure of the transaction. But I assume that the simplest way to the most of the wallets will be just having single input, single output. But if we will change the commitment scheme, this is not affected by the commitment scheme we are using. It's affected by the nature of wallet developers. It's the simplest way, one input, one output, and it doesn't matter which commitment scheme you're specifically using.
Tricola, did Maxim answer your question? Perfect.
So is there any objections of moving RGB and single-use seals from the implementation that we have for single-use seals from a pay-to-contract complex scheme to just use the first Taproot output and put of return commitment into the rightmost branch of it?
Well, yeah, going back to the questions either to keep or not also simple operator output, I was thinking about a case where maybe you may not be in a situation where you have a change address, while, for example, you need to spend all your UTXO for fees or maybe for some payment channel or something. So if you don't have a change address, you will need to create one on purpose that will maybe not have, I mean, you will just spam the UTXO set while creating one Taproot output just for commitment because you don't have a...
You mean that your input have nearly dust level of Satoshis and you put them all to fees?
Yeah, something. Yeah, for example, yeah, let's say I have 1,000 Satoshi left in my UTXO and in my input, and I need to use all of them for the fee. So even I send maybe like some dust level amount of Satoshi to Taproot output, or maybe I could just use all of it for fees and have an up return, and
right.
will avoid spamming the UTXO set.
Well, you can add another input and allocate all these 1,000 satoshis plus satoshis from the other output and like consolidate them. You can use for coin selection. So it wouldn't be a stop factor that prevents you from creating the transaction if the RGB doesn't support operator. I see another drawback of supporting operator is the fact that operator is used by different protocols today, many protocols today, and to define which of the operator outputs contain the commitment and not to collide with other protocols, like it may be also a problem. Because if other protocols will start using operator in the Taproot, they will use the protocol that we developed because basically it prevents multiple protocols to work in parallel. If we use operator, we will face to the compatibility issue with existing protocols. We just simply put the code or the commitment into operator, and it will probably create more problems than solutions.
Maxim, your screen is gone again. I think you have a bad internet connection, and this is why it just stops sharing the screen from time to time.
So I don't know, would it provide more advantages than disadvantages to support just plain operator?
Well, I don't know. Yeah, maybe I don't have a clear understanding of the I don't think he had much extra complexity to the protocol, but I think it can maybe simplify some specific cases.
There is another way forward with this question is that the actual, I already have implementation for return, so it doesn't add anything to the story. So when we define a single use seal, as Peter Todd suggested last year in the previous call, we will have a byte that will define the specific commitment protocol that is used for single use seal closing. And the 001, for instance, will define this op-return Taproot-based protocol. And the implementation will also support just this one. But if we will find any issues, because we will have some first wallets starting using RGB and playing with that, and if we will face issues that we really need op-return, we will say that, okay, now the RGB supports with a 0.02 version of the single-use seal op-return, just plain op-return commitments, and we can quite easily add it, and it will be adapted because it solves the problem. If we will find out that the problem is non-existent, we will end up just with the op-return in Taproot trees.
Oh, well, it may be a problem for some users, not for all of them. So you may end up with people that want to adopt the new version that also support op-return, people that don't care, and so you kind of split the RGB network.
Jackman, what do you think about supporting the plain op-return?
I don't know, mixed feelings. Like from an elegance point of view, probably just like we still support bare multisig, even if we move to Taproot to do multisig stuff, it could make sense. I will probably defer. It's true that it's nice to push people to adopt Taproot, but it's not really our main goal. Or anyway, we should do that with other means, not with this mean. It's probably the wrong place to put Taproot pressure. So probably I think my answer will depend on how much of actual complexity there will be in order to manage two instead of one. I think that managing op-return, bare op-return, plus a very different pay-to-contract scheme may be actually very ugly to see in code. While managing op-return with the difference that the op-return may be inside or outside a Taproot, may be possibly a little bit less messy. So you just have to assume it's an op-return, but then you just abstract away the fact that the op-return is inside a TapScript or outside. And people, of course, will be discouraged from using it outside by fee pressure eventually. So they will include it into TapScript. So I don't know. I don't have a strong opinion. I think I will be fine with both actually.
Okay, then in my implementation, I will support both. It's always easier to remove something than to add later. So probably then let's stick with the op return plus taproot based op return. Tap return, let's name it like that. So that's basically the main part of the story. There are two other small questions to discuss, which I will try to go really briefly through. There is another problem, which is not specific to op return or pay to contract. It is shared by them. Is how to construct the multi-party transaction to avoid interactive protocols. And basically, Peter already discussed that thing, and it comes down to the same idea that we can split. We have two levels of the structure. The first level is defined by LNPBP4 protocol, which allows us to put commitments under different protocols into a Merkle tree and commit to these commitments via the Merkle route. So the deterministic Bitcoin commitment with op return or tap return or any other scheme is a commitment which is a Merkle route of the commitment tree. And the list of that Merkle tree is the commitments under specific protocols. And in RGB, each RGB contract, each asset is a different protocol. So basically, if you have multiple assets in the same output, well, if you spend multiple assets with the same transaction, you will end up with independent state transitions, which you do not need to disclose. So basically, if you move some assets in a joint transaction, you just provide the hashes, and the people wouldn't even know which assets are there. So that part was solved for a long time already, for more than a year. The other part of the joint transaction is where you have inputs from different participants with the same asset. For instance, USD Tether. And in that case, you will end up to today, with the need to construct a single state transition for USD Tether that describes the destiny of all the inputs from different participants into that common USD Tether. And then, of course, outputs. And that will create two problems. The first is the leakage of information, because participants have to construct the state transition jointly and provide full history of each of their assets, USD Tethers. And so interactivity, information leakage. And the last problem that it will create a big aggregation in the client-side validated graph, ending up that the size of the client-side validated data will explode if they are put through the joint transactions, like in exchanges, for instance. And that's
screen again, not sharing.
And that's a problem. And this problem can be avoided by having the second level of Merkle tree. So basically, with LNPBP 4, you have a Merkle tree of protocols, and then each leaf is a commitment to a small Merkle tree, one per transaction input. And you will have multiple state transitions in the transaction, and the state transition can spend one or more inputs, and the commitment to the state transition should go into the second level of Merkle tree in the leaf, which number corresponds to the number of transaction input getting that asset from. I don't know, was I able to explain that idea, but basically it's the same idea that Peter was talking before, from what I got. And this allows you to have multiple state transition under this independent from each other, under the same asset in the same transaction, without the risk of double spending, because each state transition has to commit into the leaf which corresponds to the specific input. And you know that assets from that input can be spent only with the state transition that is to which the leaf is committed to. So that's the idea how we can solve the problem of the joint transactions working with the same RGB asset coming from different participants.
There is a question in the chat. So if you implement op return in addition to tap return, will Taproot support still be mandatory for RGB wallets?
Let's discuss this question after this one, because I just explained it, and I would like to hear the feedback on this question and not the previous one. And then we will go back to the op return and tap return. So Giacomo, Federico, Peter, do you have any critics on this idea?
No, I don't think so. Fede?
No, not really.
I think I'd want to double check it on a piece of paper, but it sounded decent.
Okay, perfect. So Olga, can you please repeat the question that we had?
Yes, of course. And meanwhile, you can again try to switch on the screen sharing. I have no idea what's happening, sorry. So the question was, if you implement op return in addition to tap return, will Taproot still be will Taproot support still be mandatory for RGB wallets?
No.
Well, I guess the answer could be more.
Well, if you have choice from using op return or tap return commitment scheme, you are not limited to tap return commitment scheme, and you are not restricted to having Taproot support. So that's
yeah, that will be one of the advantages. That like if you want to like quickly build a RGB compatible wallet using maybe some libraries that still doesn't support Taproot, or for whatever reason you want to avoid the Taproot in the short term, you could do it.
And is the advantage to supporting Taproot to kind of enable more intercompatibility with other different protocols?
The idea to support Taproot is to enable more compatibility with other protocols. Sorry, I'm not entirely with you.
No, well, I was.
Go ahead.
No, yeah, I would say that the advantage of supporting Taproot is that is more efficient. So you don't use on-chain space, and you also you improve efficiency and privacy. But the disadvantage is that to force Taproot is that for a wallet developer, it may be a bit more complicated, especially for the first years when Taproot is not so widespread. So that's
But a problem that I see now, sorry, this was a point to rise before, but it just occurred to me now, because we are saying, okay, you don't have to support Taproot now because you have the choice. Okay, but if the consignment that you're receiving contains a history that at a certain point used a Taproot op return as opposed to a, I mean, you still have to, I mean, you need Taproot if the assets is defined in a way that needs Taproot. So you otherwise you need.
You need to understand Taproot, but that's something that the RGB node will do. But your wallet that creates transaction doesn't need to create them with the Taproot.
So the current answer, exactly. The current answer is you need to be able to receive to understand past Taproot transaction, but you may not be able to construct Taproot. That's correct. Okay.
Yeah, but that's not a problem of wallet developer.
Yeah, it's a requirement to it's on the RGB core. So basically, it can't be extracted from RGB protocol. The RGB protocol knows about Taproot internally. It doesn't expose it to the wallet, and wallet developers do not need to add any specific Taproot support to parse the consignment that historically was going through the Taproot commitments.
Yes, perfect. Okay.
So there is the last part with the 2 slides on PSBT related stuff, how this actually will work with the wallets. And if we have any other questions related to tap return and the deterministic Bitcoin commitments, we can discuss them. If not, I will just complete the presentation with these 2 last slides. Any questions? Okay, so basically regarding the PSBT workflow, the existing standards on PSBT define clear roles, namely the first version of PSBT defines creator, updater, signer, finalizer, which is actually input finalizer, and extractor. The second version of PSBT adds to that list a constructor. And you can read the BAP standards to see how these roles interact. And they are also quite well designed. And the idea of these roles to make different complex schemes, including multi-sig setups, coin joins, multiple hardware devices used to sign the transactions by the same party possible. And they do that job well. Now, my task was to put into this workflow where the actual commitment procedure with the deterministic commitments take place. And the wallet, basically, this requires addition of special dedicated role called output finalizer. So we have input finalizer, but now we have output finalizer. And this role goes after the updater, but before the signer. Because the signer has to sign the serialized transaction data, which includes all of the outputs, and these outputs must already contain the commitment. And three of these roles will have, like two roles will have modifications related to the deterministic Bitcoin commitments, and the third role will be added to the workflow. So the creator and constructor, it uses wallet descriptor, set of UTXOs and invoice to construct the PSBT. And that is how it is defined by existing specifications. With regarding the RGB, it will not add any RGB information to this PSBT, but it will mark outputs which can contain deterministic Bitcoin commitments, which are allowed to contain deterministic Bitcoin commitments. Why? Because even if we use a fixed output number to put the commitment, like the first output, the other roles like updater may reorder outputs. So that's why this information has to be present, such that reordering if reordering is happening, the updater will be able to put the output that may contain the commitment into the proper place. It also adds information about RGB contracts, so not state transition, but contracts, because the wallets which will sign the transaction containing RGB assets will need to know about that assets, the name of assets, and so on and so forth. So the genesis blocks of the assets will be put into the PSBT at the global map by the creator or constructor. And it also, no, not construct state transition. That's wrong. Sorry, I will change that. It's wrong. So the updater takes this PSBT and fills information about RGB assets in the inputs. And it also adds information about other client-side validated protocols, if they will ever be used with the PSBT. It creates the state transition because now it knows the input assets, and it may rearrange output order, but it will take into account which outputs may contain DBCs such that they are put in the proper place. And the third actor, which we add to the workflow, output finalizer, constructs structures called anchors, which actually this whole trees of deterministic Bitcoin commitments. Basically, it creates the deterministic Bitcoin commitments and creates proof of that commitment. And it put proof into the global map of the partially signed Bitcoin transaction such that the wallet and other participants will be, and signing devices will be able to extract it and save locally or add to the RGB stash. So that is the workflow. And these are the fields, the keys that are added to global input and output maps of the PSBT with specific types, keys, values, and definition who adds them or who can edit these fields. So on the global level, the creator adds information about RGB contracts, keyed by contract ID, and represented by Genesis block. And the updater creates a state transitions, one per contract ID, and potentially with an input number, because there can be multiple state transition in the same transaction, one per input, and the actual transition as a value. The inputs contain the information about the previous state transition that provides input to this transaction, also keyed by contract ID. And there might be multiple transition because the same UTXO may contain multiple single-use seals from multiple transitions. And outputs will have a marker flag of which output can contain commitment put by creator or constructor. It will contain the LNPBP tree, Merkle tree, or the root of that Merkle tree, put by the output finalizer. This Merkle tree is the tree of all commitments on the different protocols. And for instance, if the PSBT will be used with the open timestamps, for instance, OTC root commitment can go here. And finally, when the output finalizer creates the commitment and the proof, it puts the proof of the commitment into the output field, into the output that contains the actual commitment. So that's the PSBT workflow. And that's all for today. Are there any questions related to PSBT processing?
Well, frankly, I got to read up more about PSBT to have more questions, but it sounded good.
Thanks. I
Same.
will do a reference implementation of all this story over the week or 2 weeks, and also write up the standard such that there will be a code, Rust code, and the standard, and I will ask to review this code and the text. That would be probably the best way to continue this discussion. It's very unfortunate that nearly 3 years after the start of the RGB development, we have to change the foundations of the commitment schemes. Thanks to Taproot, it gives us that opportunity.
Well, I mean, it looks much better right now compared to the first pay-to-contract. It looks much more like simple and elegant. So quite
Yeah,
Yes,
also, I
go on.
really ended up disliking the fee part. I don't know. I was on board at the beginning, but but going forward, I was really growing to hate the fee tweaking.
Yeah, the main problem that we didn't discuss like back in the days, but that I saw like in the presentation today, that the fact that you need an indexer node is very, very bad. I mean, it's very limiting for a lot of wallet application.
Yep.
I was shocked by the complexity of doing this stuff in the real world. I mean, pay-to-contract and fees. It made the code of the wallet so much complex and recursive even, that it was crazy how to debug it and do a real good user experience with that.
So does Taproot simplify, in a way, the wallet
Yes.
implementation?
Yeah. Yes, it simplifies much because, first of all, you don't need to tweak the keys anymore, and you don't need to tweak the private keys to do the signatures anymore, and you don't need to adjust the fee. Well, it's not part of the Taproot improvements, but still, it's a part of the improvements that we can put back all together since we're already changing commitment scheme.
That's good to
And
know.
all,
Also,
yeah.
Go ahead.
Yeah, and all commitments are going to a single output, which also simplifies the wallet part.
That's good to know. Also, how dramatic are the space improvements, would you imagine, on-chain to be?
Well, there is no space improvements on chain by itself because pay-to-contract was putting the commitments into the public key, so there was no space consumption. And there is no space consumption with the operator in Taproot. So basically,
Gotcha.
on-chain space is not affected. It's the complexity of the wallet software that is affected.
Makes sense. Okay. Good call. Thank you.
And also the PSBT modifications required to pay to contract, which I was designing through the last year, are much, much complex, more complex and risky than the one that are required to top return commitment scheme. And actually, I wasn't able to finalize that design throughout, like, at least half of the year. I was discussing it with Andrew Pelstra and others, and there still were pending questions or security risks which were not addressed even after a long time analysis.
Well, basically, I will brutally summarize this as the whole Bitcoin protocol is moving to pay-to-contract itself. So we just tag along instead of reinventing it for a separate use case.
Yeah, kind of that story, yes. Thank you for joining the call today.
So wait, yeah, I have one last question that is unrelated to everything that we discussed today, but I wanted to ask you, like, is there already any like proposal for a proof of payment mechanism? So if I send you a RGB token, I can prove beyond doubt that I actually sent you, like, you cannot deny it.
I cannot deny it, but I can deny that I have received that proof. And not, can you define more precisely what is the proof?
Okay, let's say that. Okay, I send you. I send you RGB assets. So I create the RGB transaction. I commit in to XO. I send, and then you simply say, "Oh, I never receive it." And then if we need to have a dispute, I'm not able to prove that that you actually received it. Something like this.
So can you prove against the third party that the payment?
Yeah, exactly. Can I prove against the third party that I sent you the assets?
Yeah, the consignment, the RGB consignment, which contains the client-side validated proofs of the history of the asset plus the last state transition, is that way to prove that. Like Bitcoin transaction plus blockchain is the proof of Bitcoin being sent.
No, but the thing is that, like, I could send you on the other way. I could send you asset, but not send you the consignment, and so then you destroy your UTXO and you lose the asset, and you say, but you never send me the consignment, so you send me asset now or destroy it's your fault, and then the other party say, no, actually I sent you the consignment, something like this.
No.
Okay. I have some ideas for that.
It is possible with interactive protocol. So you first send the consignment, and then you got the signature of the payment receiver that he got this consignment, and then you mine the transaction.
Yeah, indeed. Right. Yeah, I wanted to propose that.
Yeah, but it will.
But basically we will move to some kind of payment protocol extension, some kind of. I think this discussion in a way interacts with offer discussion, Bol 12. So it's the whole thing that the receiver should not just receive asset randomly without being able to read. So probably if they countersign that they received, that's better.
Yeah, no, I think it's very important because in this case, you actually end up destroying asset while in Lightning Network, at least the Bitcoins are not lost. So yeah, I think it's something that can be quite important.
Yeah, I agree.
Okay, so maybe I will try to formalize a proposal in a GitHub issue so we can have,
yeah, that would be great.
Okay, so that's it for me.
Probably, I think that the workflow should be the following. When I want to receive a payment from you, I create an invoice. We already have a standard for invoice. It's working with RGB and Lightning Network. And I sign this invoice with my signature. And in that invoice, I also provide the address to which the consignment has to be sent. And this address is also signed. So when you're doing the payment, you know that you have to sign the consignment to this specific server, Bifrost server. And you do that, and Bifrost server responds to the consignment with a signature. And now, as a sender of the funds, I have your signature as a payer to trust this specific server that receives the consignment, and I have a signature of the server that it indeed received the consignment for the payment. And after that, I publish the transaction containing commitment to that state transition, the last state transition. And now I can prove against any arbiter that actually I did everything right, according to your instructions.
Yeah, indeed. The important thing is that to have a proof that the consignment data was received before you do the Bitcoin transaction.
And validate.
Yeah. Okay.
And we already have interactive protocol with the consignment being sent, so it doesn't actually add more interactivity to that scheme.
Yeah, you just add some sort of reply to the consignment that is been sent.
Just in Bifrost protocol, I have to put that the server has to respond with a signature of the consignment, and that the wallet actually has to publish to mine the transaction, to publish the transaction with a commitment to the last state transition after sending the consignment and receiving the signature.
Yes.
Perfect. Any other questions to discuss today, or we're done?
I guess we're done.
Yeah, maybe we can wrap this up if no one has any questions.
Nope, sounds good to me.
Thank you.
Thank you, everybody. Good night.
Thank you.
Or
Good
day.
night.